Okay, good morning everyone and happy 1st of May. Today's talk is about the Jacobi vector fields and it is divided into three parts. The first part is about the Jacobi fields in Riemannian geometry, and the second part is about the connection between Jacobi fields and the variations, and the third part is about the conjugate points. So we start by reminding some things by the Riemannian geometry. Throughout this talk, we have a Riemannian manifold equipped with a Riemannian metric G. The dimension of our manifold is equal to n, and we have as the nabla the Levi-Civita connection. We remind that is the only connection that is compatible with the metric and has zero torsion. And also, by having the connection, we can define the Levi-Civita connection. We can define the Riemann curvature tensor here by this formula for all vector fields x, y, and z on M. So we have the local formula for the Riemann curvature tensor here by choosing a canonical frame, and these are the coefficients of the Riemann curvature tensor. We can see the connection between them and the Christoffel symbols, and also the derivatives with respect to x, y, and xj of the Christoffel symbols. And by this formula here, we can see that the Riemann curvature tensor offers a measure of non-commutativity for the Levi-Civita connection here by using this. And also we have a covariant derivative for all vector fields along a smooth curve on M. Let call the curve gamma. So this is the definition of and the notation for the covariant derivative. It satisfies the Leibniz rule and it is compatible with the metric here. And following this notation, the Gothic x of gamma, we have practically all the sections of the pullback bundle of Tm by using gamma. It is practically the discrete union of all the tangent spaces of M, but along the spaces of over the points of gamma. Here we have an example. If our manifold has a constant sectional curvature, the formula for R can be simplified into this. For the Rn, the Euclidean space of dimension n, we have that k is equal to 0. And for the n-dimensional sphere of radius r, we have that the constant sectional curvature is practically equal to 1 divided by the r square. We remind also the definition of a vector field which is parallel along a curve. It satisfies this condition here. Practically, the covariant derivative of x along gamma is 0. And we can see by the definition of a Riemannian geodesic, because the covariant derivative of the velocity field is equal to 0, we can call the alternative name autoparallel curve for a Riemannian geodesic. Also, here we have another example by starting with a hypersurface sigma on M. The dimension of sigma is n minus 1. We have the unit normal vector, and also we can define an induced Levi-Civita connection on sigma. Here, this is the Riemannian structure of sigma. The natural way to define the Levi-Civita connection on the hypersurface is this, using practically the tangential component of the nabla x and y. Here also we can define an induced covariant derivative on sigma practically, and this is the formula of the covariant derivative is that also the tangential component of the covariant derivative on M. Here we have the usual shape for this case. We have a visualization practically of the covariant derivative of the vector field W along a curve gamma, which is into a hypersurface sigma on M. We remind also that for a Riemannian geodesic, practically the covariant derivative has only normal component. Here, the coefficient is the normal curvature, and we need some facts and some interesting properties of the Riemann curvature tensor, which will be used later. here the antisymmetry using the first two arguments, and this is the first Bianchi identity, Jacobi type identity here for R. And now we can go to the definition of a Jacobi field. We start with a Riemannian geodesic gamma on M, and the vector field X along gamma is Jacobi, is called a Jacobi field if it satisfies this equation here. This equation is called the Jacobi equation, and only this term can be called the Jacobi operator. Following our previous notation, we can denote this term as the square of the covariant derivative, and practically we can transform the equation using these notations into the equivalent one. And what is this equation? From an analytic point of view, we can interpret this condition, the Jacobi condition, the Jacobi equation of a Jacobi field, as a system of n linear second-order ODEs. We can see the construction and the depiction of this. We remind that if we have a Riemannian geodesic gamma defined on a closed interval AB, we have the starting tangent space here, which is equipped with an orthonormal frame, and by solving the system of these first order linear ODEs with initial conditions, we can see that we have an induced orthonormal parallel frame by using the compatibility with the metric of the covariant derivative. So every vector field X along gamma can be written as a combination of this orthonormal parallel frame here. Also by using the compatibility with a metric, because each EI is parallel, we can see that here it's the expression of the covariant derivative and the squared covariant derivative. And we can denote the second term in the Jacobi equation here as this. So the Jacobi equation takes this form, which is practically a system of ODEs, and using the initial data, we can see that also this is a system of n linear second-order ODEs, which can be solved by the uniqueness and existence theorem for ODEs. We have many examples of Jacobi vector fields. The velocity field of geodesic, the velocity field is a Jacobi vector field because it satisfies the Jacobi equation, because we have a geodesic, practically the covariant derivative of the velocity is zero, and also using the antisymmetry of the Riemann curvature tensor, we have that here this term in the Jacobi equation is zero, so the Jacobi equation is satisfied. Also, we can see that every multiplication of the velocity field by t is also Jacobi by using the condition of the geodesic. And another example here of Jacobi fields on the Rn, because we have the geodesics of Rn are lines, we have a trivial Jacobi vector field by solving the system of ODEs, which is of this form. And another example is every x along a geodesic that satisfies this initial condition, which is of the form, which is a combination of v and w, which are parallel along gamma. Also, here we have a decomposition for every Jacobi vector field along a geodesic. That Jacobi field decomposes into two components, the tangential and the normal one. And because we can choose as E1 the velocity field, we can see that the tangential decomposition is of this form here, and also the tangential part of the Jacobi vector field, and also the normal component is of this form. But by solving the differential equation for the first coordinate function by using the Jacobi condition, we can see that the first function is trivial for the tangential part. So the tangential Jacobi vector fields are of no interest, and we need the normal ones practically. And what is a normal Jacobi field along a geodesic is normal if it belongs in the normal bundle along gamma, which means that it practically is no, is normal to the velocity field. And we have another example. If our manifold has constant sectional curvature, like the n-dimensional sphere, let's take of radius r, then the normal Jacobi fields satisfy these equations here. The system of our ODEs is simplified, and we can solve it. The solutions are of this form here, which will be used in another example later. For example, for the Euclidean case, for Rn, k is equal to 0. And then in our second part, we have the Jacobi fields and the connection with the variation, with a variation. But let's remind what is a variation. In what follows, we have an arc length parameterization for our curve, and S is the arc length parameter for a geodesic. We remind that a variation, let's call it gamma capital, is practically a paramorphosis of the starting curve, a family of curves which can be seen as transformations of the first one by a parameter t. The starting curve is called the basis of the variation, and we denote by t of s the velocity field of the starting curve, and the Vs, defined by this formula here, is the variational vector field. So we can compute the length of a variational curve, gamma t, and its energy by the usual formulas here, the formula for the length and the formula for the bending energy. So we can also compute the first variation of the length and the first variation of the energy, which are equal here. For what follows, we let the endpoints of the variation to be fixed practically. So it's like having an oscillation of the starting curve. That means that the variational vector field to the endpoints A and B is equal to 0. And then this term here vanishes. And so the formula for the first variation of the length and the energy can be simplified into this equation number 4. So by the equation number 4, we can see that geodesics are the critical points of the two functionals, something that is known from the Riemannian geometry. And also we have the formula for the second variation of energy here. Also by choosing fixed endpoints, the formula can be simplified to the equation number 5. And combining with the compatibility with the metric, this term here is equal to this integral of the inner product. And finally, by combining equation number 5 and 6, we have that the second variation of energy is equal to this. So we have here this term, which is practically the Jacobi operator, and we can see the connection of the second variation of energy with the Jacobi vector fields. Now we define the index of a variational vector field, which is the second variation of energy, and we choose the endpoints of our variation to be fixed. So we can define the index with two arguments here by using a two-parameter variation and another variational vector field with respect to the variational parameters t and r. So the index is defined for v and w, and for an arc length parameterized curve, we denote as Gothic x, gamma, and 0 the set of all vector fields x along gamma that vanish on the endpoints here. And following these notations here, we can interpret the index by using this definition here from equation number 7 as a bilinear and symmetric form by seeing here this definition. And we have a proposition. A vector field is a Jacobi vector field if and only if the index vanishes for all w in this space, and it follows by the fundamental lemma of the calculus of variations and the definitions and the compatibility with the metric. Again, also after integrating by parts, we have this corollary here that a vector field is Jacobi, another equivalent condition, if it is a critical point of the functional of the index functional here. And one of our main theorems is this, that by starting with a variation through geodesics, meaning that every variational curve is geodesic with the endpoints fixed, to this we can call a variation with the endpoints to be fixed as a proper variation. So we have that the variation vector field is a Jacobi field along the base curve, and also the converse is true. Every Jacobi field can be obtained by a variation through geodesics. Here we have another theorem that connects the Jacobi field with the exponential map. We start with a geodesic gamma and defined in an interval here of this notation. We start at the point P with velocity v, this condition here. So the geodesic has a parameterization of this type. And for all vectors W inside the tangent space over P, the Jacobi field X along gamma with these two initial conditions can be given by this formula, here using the differential of the exponential map at over the point TV here. And we have this corollary for a point P on M and a vector V inside the tangent space that can be contained in the domain of the definition of the exponential map. We have a line segment of this form and its image using the exponential map over P. And for every piecewise smooth curve contained in the domain of definition of the exponential map, such that it satisfies this condition, the following inequality holds, and that connects the length of this curve here and its image and the length of the image of this curve using the exponential map, and the equality holds if the curve tilde c is a reparametrization of our starting line segment. So now we can present the conjugate points. Here we have the definition. We start with Riemannian geodesic gamma on M, and for two different times, let's call them T0 and T1, the points gamma T0 and gamma T1 are called the conjugate along the geodesic gamma if we have a Jacobi field that does not vanish identically, but it's zero in the T, it's zero over the points gamma T0 and gamma T1. So by starting with a Jacobi field of this, by starting by such Jacobi field, we have that it's always normal to gamma because of the decomposition, and using the Jacobi equation and the initial conditions given by equation 9, we can see that the tangential component is 0 by using that x of T0 and x of T1 is 0. So a Jacobi field of this type is always normal to the geodesic gamma. We have examples. On Rn there are no conjugate points. The same holds in general on Riemannian manifolds of non-positive sectional curvature. On the n-dimensional sphere of radius 1, a Jacobi field along a geodesic where S is an arc length. We remind that geodesics on the sphere are great circles. A Jacobi field with conjugate points is of this form here. So we can see that the definition of conjugate points at times S0 and S1, because we have an arc length, leads to this system of differential equations, and the only non-trivial solutions of this system are given if only if the difference of these two times is an multiplication of PR by an integer k, which means that the 2 points, gamma S0 and gamma S1, are adipodal or are identified. So we have here this theorem, also one of our main theorems, that states the geodesics with no conjugate points are locally minimizing among nearby curves with the same endpoints. This is the locally minimizing property. But the existence of conjugate points let this property to fail here. So the geodesics fail to be locally minimizing. And we have that this corollary, when gamma is geodesic on M, there is no pair of conjugate points along gamma if and only if the index form we have defined is positive definite on the set of vector fields along gamma that are zero at the endpoints. We can keep the space of these vector fields with a norm defined by this formula here, and also we denote its completion by this set here. It's the closure, and using an orthonormal parallel frame, the definition of the norm for this set transforms into this one. So we have the following identification between Sobolev spaces, and we can consider again the index form as a quadratic form induced by the bilinear and symmetric form of this type here, given by the formula number 10. So we have the definition of the index of gamma, and what is the index? Is the dimension of the largest subspace of this set on which the index is negative definite, and the extended index of gamma, notated by this one, the index 0 of gamma, is the dimension of the largest subspace of this set on which the index is negative semi-definite. And we have a definition for the nullity of gamma, which is the difference between the two indices here. The index of gamma and the nullity are finite. And for a random t in this interval, we define by j gamma t this set that are all the vector fields along gamma that are Jacobi and vanish at the points a and t. And practically, this set is non-trivial, is non-zero subspace, if and only if the points gamma and gamma t are conjugate by the definition of conjugate points at a and t. Also, the kernel of the form is the space j gamma b, and the nullity of gamma is the dimension of this vector subspace. And finally, we can derive the Morse index theorem. Let's call it MIT, not the usual MIT. But we have this theorem, and the main theorem, the Morse index theorem, states that if we start with a Riemannian geodesic gamma, then there are at most finitely many points conjugate to gamma A along gamma, and the index of gamma and the extended index of gamma can be given using these formulas here, and we can calculate the index on the example of the n-dimensional sphere of radius 1 here by this type here, because we have also every time a conjugation. And thanks. That's all for today. Thank you for your attention.